Swayam Prabha. Digital India. Educated India.
So in today's lecture, we'll be talking about the single phase AC circuit. So as we know that the AC circuit already gives an idea, which means that a kind of circuit which is having the variation of voltage in the current in a sinusoidal form or the AC form, then those circuits are known as alternating current circuits or AC circuits. So basically the quantities voltage and current will vary sinusoidally. Okay, so V will be as a function of time or omega t, you can say that is a secondary. So it will be of the order of the form of sine omega t plus phi, and the current will be of the form of, these are the form of voltage and the current, basically the sinusoidal, which will be present in the circuits. So in these circuits they are considering the combination of resistance, inductance and capacitance. So in this AC circuits we'll be having a combination of R, L and C. So the source which will be feeding some combination. So this is suppose represents some R, L, C parallel, series parallel or any kind of combination which is represented by Z. So this is V and the current which is going is I. So V is nothing but a sinusoidal quantity. Suppose phi, which is represented as V, suppose V bar angle of phi. This is a phasor representation, correct? Similarly, the I, which is represented as Im sine omega t plus theta. This is nothing but I phasor. Okay. So the quantity Z is known as impedance. First we'll define that impedance. Okay. So impedance is mathematically defined as the ratio of voltage phasor to the current phasor. Okay, so Z is basically defined as the voltage phasor and the current phasor. So if we have a kind of representation mathematically, we'll be having V angle or V5 angle phi divided by I phasor angle theta. So this is basically the impedance. Okay, so we'll be having impedance which is defined mathematically in this form. So if we talk about another quantity like inverse of Z, that is known as immitance, which is represented by Y and which is nothing but 1 by Z, or we can say I phasor divided by voltage phasor, where these are the phasor quantities and represent the RMS values. So I bar and V bar are RMS values. Okay, so these are the quantities which we should be understanding before going to the circuit part. Okay, now one by one we'll be considering small examples of R and C and see the behavior in terms of their phase differences of voltage and the current and their mathematical form. So let us consider the pure resistive circuit and see how it behaves to the the AC supplies, because we'll be seeing that. So consider the purely resistive circuit. Okay, so in purely resistive circuit, the source will be feeding to a resistance. So we have a source, AC source, which is feeding a resistance, which is represented by R, and the current is suppose I and the voltage is V. These are the phasor quantities. So let us take the supply. Vs is nothing but Vm sine omega t, which in phasor form is represented as like in phasor form it is represented as E angle 0, correct, where V bar is nothing but Vm by root 2. Is it okay? Yes. So now we'll be applying the Ohm's law, correct. So when we apply the Ohm's law, the current which is flowing, okay, the current, suppose IR, the current through the resistor, so this is the current through the resistor IR, is nothing but Vs, the voltage supply divided by the resistance. It means that Vm by R sine omega t from here, correct. So if we represent this as this sine omega t, where this Im is nothing but Vm by R, and if we want to represent in phasor form, it's very clear, right? It is nothing but the I phasor angle again 0, correct, and I phasor magnitude is nothing but the RMS, which is Im by root 2. So this is a representation, this is RMS value, right? So here we have seen that the voltage and the current are having the same angle. It means that in pure resistive circuit, the voltage and the current are in same phase. So if we see the impedance, the Z will nothing but the voltage angle 0 divided by current angle 0, which is nothing but the R. Okay, so this is what we have seen in case of the pure resistive circuit. So if we represent Z in the complex form, so we can write Z is nothing but R plus J 0. This is nothing but 0. Okay, imaginary part is 0 and the real part is Z R. So if we see graphically, there is a voltage which is sinusoidally varying on the axis of omega t. Here the, suppose we are representing this as a voltage magnitude. Okay, this is pi and this is 2 pi. Okay, now if we see the variation of the current, which will be having the same phase, right? So it is in the same phase. and the peak value will go to Im. This is Vm. So the peak value will be Im and the phase will be same. So this peak will occur at the same time, which will be pi by 2, and this peak will occur at the same time, which will be nothing but 3 pi by 2. And if you want to represent these quantities in the phasor form, so this will be the voltage phasor as reference, then there will be some current phasor. Okay, this is your origin, so they will be in the same phase. So this is the representation of mathematical form, the graphical form, and the phasor form. So, and again the voltage across the resistor, VR is nothing but the voltage across the resistor will be nothing but the R times of the current passing through the resistor. Now this IR is basically the phasor, which is I angle 0. So this is in the form of Ohm's law. Okay, so hope this is clear, the resistive behavior in the case of AC circuits. So now we'll see the inductive nature of the element. So we'll be considering about the purely inductive circuit. So when we consider the purely inductive circuit, we'll be having a source which is feeding nothing but an inductor, correct, which is a pure inductor L. So in case of an inductor, we know that whenever the current passes, it induces a self-induced EMF, right? So if suppose the current I, or here if we see IL, and the voltage is V, the phasor, so the induced voltage, okay, the self-induced voltage will be nothing but, and this I is the IL, the current which is flowing through the inductor, and the negative terms, this sign comes from the Lenz's law, which opposes the cause which makes it to flow, or okay, so the current IL, so dIL by dt is the self-induced EMF. So it means that there is some voltage which is appearing across EL, and if we apply the KVL in this loop, we know that the, so first is the supply voltage, right, VL. Suppose this is IL and assume this is VL. If we apply the KVL, okay, we apply the KVL in this circuit, so we understand that VL plus EL is nothing but 0. So EL has to be, sorry, this VL supply voltage, right? So if we assume this VL is nothing but negative of EL, which is L dIL by dt. Is it clear? Now pay attention, if we assume that the current through the inductor is of this form, so assume current flowing through inductor is IL, where IL is given as Im sin omega t. Okay, so then what is the VL? VL is nothing but L d by dt of Im sin omega t. Is it clear? Now here a very interesting thing will be seen here. So this will be omega L Im cos of omega t, isn't it? So if we represent this quantity as Vm, right, is in the form of sine omega t plus 90 degree. This is basically the supply voltage which was applied across the inductor. So here we clearly see that there is some phase difference. This is nothing but phase difference. When we see this, Okay, now write the IL, the current, in the form of phasor. So the current phasor IL can be written as I angle 0, and the voltage which is applied across the resistor, the inductor VL, is written as V angle 90. Is it clear? So here I is nothing but Im by root 2 angle 0, and V is nothing but Vm by root 2 angle 0, not 0, 90. This, sorry for this, this is angle. Okay, here clearly we can see that there is a phase difference of 90 degree. Now draw the phasor diagram first. So if we try to draw the phasor diagram, we see that the reference is current I, okay, and voltage 90 degree positive, so anti-clockwise if we take positive, so this you see the voltage phasor. Okay, so this is how the phasor diagram of purely inductive circuit will look like. The voltage and the current will be having a phase difference of 90 degree. Now if we see the waveform, so let us draw the waveform and see how the waveform is looking like. So we have a current which is varying in this form of sinusoidal waveform. Okay, so this is what the phase current waveform. Now if you see the voltage which is having a positive 90 degree, this phase, so it will be having maximum at the 0, maximum at the 0, it will go here, and the maximum will be here. Basically, so I'll just, this is the this, you see, this is nothing but the voltage phasor, and the peak value is Vm, and this is voltage phasor, or the V, small vl, this is IL. Okay, so here if we see, in case of pure inductive circuit, the current lags behind, right? The current lags behind the voltage by 90 degree. It is reaching the first 0 before pi by 2. Okay, so in the case of purely inductive circuit, the current phasor lags the voltage phasor by 90 degree. So here if you try to find out what is the Z, the impedance, so impedance is defined as the voltage phasor divided by the current phasor, right? The voltage phasor V by the current phasor, so which is nothing but the V angle 90 degree divided by I angle 0. There you see it is nothing but VL by IL, or V by I. What we have defined, V by I angle of 90 degree. Angle of 90 degree. Correct. So, and the VL by IL is nothing but from where? So if you go up a little bit from here, Vm we have defined as omega L into Im. So if you do by root 2 here and then by root 2 here, then we'll find from, okay, I'll write on the top side. So Vm by root 2 is nothing but V omega L into I. So V by I, so this is nothing but V by I if we calculate, that is right directly. So V by I is nothing but omega L. So from here if you come down, So V by I is nothing but omega L. Okay, angle 90 degree, correct. So suppose this is represented by XL, the reactance. X is for reactance, L is inductive. So basically the inductive reactance, and angle 90 degree is basically the J. Okay, so we defined as the inductive circuit, ZL is nothing but the J omega L, which means JXL. This will be seen actually very frequently when using the AC circuit. So it will be useful when we'll be seeing the combination of R, L and C. So if we write this, ZL real is 0 plus imaginary part is omega L, or 0 plus JXL. So this is the kind of representation of impedance, correct. So again we have omega nothing but the 2 pi f. Okay, so that will be seen. And if we in terms of Z, if we try to form the voltage across the inductor, which is nothing but j omega L, right? So the RMS, if we calculate, suppose RMS is the voltage across the inductor, is nothing but the XL. So j omega L I, this is the volt and the current relationship in terms of inductive parameter, or basically the XL. So JXL IL means the inductive current. Okay, so this is the Ohm's law for a purely inductive circuit. Now let us consider one capacitive circuit, and then we'll see how the combination of this circuit works. So now purely capacitive circuit. Okay, now purely capacitive circuit. So consider a circuit where a source which is supplying a capacitor of value C. Okay, and the voltage across C, suppose it is a VC and the current is IC. Okay, so suppose VC is nothing but Vm sine omega t. So this is the VC, the supply voltage which is across the capacitor, then the current which is flowing through the capacitor, nothing but the C dV by dt, right? The voltage across this is the VC, so this can become like this. The current IC is nothing but C dVc by dt. Okay, so if we solve this, we can clearly write C Vm omega cos of omega t. So if we represented this as Im cos of omega t, so this Im in capacitive circuit and the Im which was considered in case of resistive and the inductive circuits are different. So do not get confused, because those are the different element. So here if we see Im cos omega t is nothing but IC. So we can write as sine omega t plus 90 degree. Okay, so from here we have first assumed what, that Im is nothing but omega c Vm. So we'll be using this equation later, and then we can write in terms of phasor, right? Now the phasor VC phasor, if we write, we can write is V angle 0, and the IC current phasor, if we write, we can write I angle 90 degree, right? Because this is having a positive 90 phase difference, and this is nothing but Vm by root 2 angle 0, and this is nothing but Im by root 2 angle 90. Now from here, if we try to calculate the impedance, okay, if we're using these, if we try to calculate the impedance, which is mathematically defined as V phasor by I phasor, so here we see the capacitive component, it will be nothing but V angle 0 divided by I angle 90. So let us solve this. We can get as a V by I, and this we will be forming as minus of 90 degree. So from here, if we do, then root 2 I is nothing but root 2 times of omega c v. So root 2 से root 2 cancel, so we can get I as omega c into v. So we can write as 1 by omega c and angle 90 degree. So this is our z. So here interestingly we'll be seeing that the z, the impedance is coming out as 1 by omega c angle of minus 90. So from here if you see z, we can write as 1 by omega c angle of minus 90, which is nothing but minus jxc. Okay, so x is basically the capacitive reactance, so it can be written as minus j by omega c. So z, if we write in the form of 0 real part minus j of xc, or real part minus j of omega c. This is representation. Now if we try to draw the phasor, okay, if we try to draw the phasor, we see the reference as V, and the current, this is V angle 0, and the current is I angle 90, right? So the current I is I angle 90. The voltage phasor is nothing but V angle 0, and the current phasor is nothing but I angle 90 degree. So we can clearly see in case of purely capacitive circuit, the current leads the voltage by 90 degree. Here you can see. Okay, so from these phasors we can identify these facts. Similarly, we can, if we draw the waveforms, we can clearly see the same thing from the waveform as well, because it will follow the same leading pattern. So if we have our voltage phasor, this is 2 pi, this is pi, and this is 0, and if we try to draw the current waveform, which is I angle 90 degree, that will be suppose 90 here, and this and this. So this will be the maxima, so this will come like this, come like this, and this will be like this. So this value will be Im. Okay, this pi by 2, this is 3 pi by 2. So current leads the voltage. So sometimes it's very confusing and difficult to remember that what quantity leads the what voltage in which kind of circuit. So there is a trick to remember this. So we'll be having a trick which is nothing but C I V I L. Okay, CIV is basically, and then VIL. So CIV. So in capacitive circuit, I leads voltage. I leads V. The current leads the voltage. Similarly, VIL L means inductance, right? So in inductance, voltage leads current. Okay, so this is the easy trick to remember. Civil. So civil means capacitive current. I leads V. In case of inductive currents, V leads I. Okay. So if we write in a clear way, this is try just to make you remember this fact. So if we write clearly here, so from this side lead. In capacitive circuit, I leads V. So this part is done. Now look at this part. In this part we can see that voltage leads current in L means inductor circuit. So I have just tried to repeat the same thing so that you can remember clearly in which kind of circuit which quantity leads the other quantities. Okay, so in case of the AC circuit, the circuit law in frequency domain also holds. What it means that the Kirchhoff current law is the phasor sum, and the voltage current law turns into be a phasor sum of the voltages. So all the Kirchhoff and current law is valid provided that the quantities will be replaced by the phasor quantities. Okay, so if we talk about the series AC circuit or the parallel AC circuit, so in series AC circuit the current will remain same. Okay, so the total current will be nothing but the total voltage by the total impedance. Okay, or the impedance will be the series impedance if we'll talk about. So in case of like a series resistance, we used to have R1 plus R2 plus R3, right? Similarly, if we have for example impedance, right, Z. So suppose some circuit is there, so Z1, Z, these are basically the rectangular representation of different element. Okay, and then you have some kind of voltage which is appearing across this. There can be other element also, right? So voltage and current is passing. So basically the I will be nothing but V1 by Z1. Suppose across this the voltage is V1, then across this the voltage is V2, across this voltage V3. So I is nothing but V1 by Z1 or V2 by Z2 or V3 by Z3. Because in series the current will be same. So current across this will be current which is passing through this element Z1 will be V1 by Z1, which is I1. This is from Ohm's law. So if we talk about the impedances, right, then total impedance. What is the total impedance? So if we write about the impedance from or between the terminal A and B, the net impedance between the terminal A and B, between A and B is total, which is nothing but Z1 plus Z2 plus Z3, which is series combination. Similarly, the phasor sum of the voltage drop is equal to the applied voltage. So in case of V1, V2, V3, it is basically the phasor voltages. So sum of phasor voltage. So V is nothing but V1 plus V2 plus V3. So this is the supply voltage, and it's also be in the form of, sorry, this also be the form of a phasor. This is supply voltage. So if we assume this is a supply voltage, this is how it is going to behave. Okay. So this is also kind of having angle and magnitude both. So the phasor addition, phasor sum of the impedances in series. Similarly, the total voltage will be the phasor sum of the voltage. Okay. So if we consider a kind of series RLC circuit, for example, here only we have different components. For example, series RLC circuit. Just to understand the fact, so we have R, we have L, and we have C. This is a series circuit, right? And we have applied the voltage. The current I is flowing. So there will be some only one current which is flowing. Then we will be having VR, then we will be having VL, and then we will be having VC. Correct? So if we apply in this way, so VR, VL, and VC. So if we see the phasor VR and I, that will be like VR and I. Or magnitude can be more or less, but the phasor angle or the phase angle basically will be this same because it is a resistive component. Now we see VL. If we see VL here, the current will be lagging, that will be I. And if you see VC, this is VC, then the current will be I. This is 90 degree, this is 90 degree. This is how we can see from here, correct? So here if we see the phasor sum, okay, so the voltage which is applied, Vs, so Vs for nothing but the VR plus VL plus VC. So all these three phasor sum voltage will be equal to the supply voltage. This is what we mean to say in RLC circuit. Okay. Now what about the Z? That is nothing but V supplied by I in the phasor form. So if we say VR, we can first write separately. So VR is nothing but I into R, and VL is nothing but J omega L into I, and VC is nothing but I by J omega C, or minus J I by omega C. So this is how it will be written. Now if we see the total voltage, okay, so let us rewrite here. So here we can write it is nothing but I into R plus J omega L into I plus minus J by omega C into I. Okay, so this is basically I, you can not get confused, into I by I phasor. So this I basically also is the phasor quantity. So this Z will be nothing but R plus J omega L minus 1 by omega C. This is the Z, this total impedance. So this is nothing but J times of XL minus XC. So basically R XL XC. This is 90 degree and this is 90 degree. This is the Z representation or the net reactance. So basically the difference in the y-axis, which is XL minus XC, and the resistance, which is in the phase of the voltage. So this is the total impedance. If we talk about the magnitude of Z, is basically the R square plus XL minus XC whole square root. That will be the magnitude. And the total voltage V is nothing but Z into I, which is from here you can see the phasor terms. Okay, so V phasor, so all these quantities which we are talking is basically the phasor quantities. Okay, and if we see the magnitude of Z, as I mentioned, it is nothing but the and if we see the phase, the angle, or we can write the phi, which is nothing but this. Okay, this is 10 inverse XL minus XC by R. So the angle of the impedance phi is the angle between the I which the current leads, no, the current lags behind the voltage, because we are considering with respect to the inductance L. So it is XL minus XC. Okay, so basically the current lags behind V. So the impedance is not a phasor quantity, it is basically a complex quantity. Okay, so the phasor quantities are voltage and the current, because they are associated with the, we have seen the input voltage right earlier, so we have taken the current and voltages as a phasor, and Z, which is impedance, is not a phasor quantity, it is basically a complex quantity, so it has a magnitude and the angle.